So start your session.
So welcome to this second live session of this course, Computer Vision. And so far what I understand that almost all the topics are covered except the last topic on deep learning. So Ankita, today, do you have any specific questions from the participants or those who have participated?
No, sir. There are no specific questions.
Okay. So in that case, let me just initiate a discussion on a particular topic that is uh, on the dimensional reduction of the data. So uh, how you are, what are the techniques for reducing the dimension of a data? Uh, that is, I think, the thing that we have covered in the that was let me check. Yeah. Yes, it was probably the last week itself. It has been covered, or presently these lectures are going on. And there, the concept of principal, component analysis. Many of you already might have gone through it. So just let me discuss a few points on principal component analysis. That why this analysis is uh, useful in reducing the feature dimension of a data. Now, there are two concepts that is involved here. I think I can use a right, I can use a whiteboard. So there are two concepts which are very useful in this case. The concept is that what is the uh, dimension of the space where the data is represented, and what is the dimensionality of the, I should say, the dimensional, or what is the requirement of for the minimal requirement of a I should say, what is the minimum dimensional space that is required to represent the data. So let me give you one example. Suppose I have a three-dimensional space. As we know that it is easier to just comprehend a three-dimensional space, which is the space on which we move, and consider a plane in that space. So suppose there is a blackboard or any kind of planar sheet. Now, if all the points are in this plane, that no, you can consider these points are can be represented also a point in the three-dimensional space, which means every point will have a three-dimensional coordinate. So if you have three axes to denote this three-dimensional space, three coordinate axes, mutually orthogonal coordinate axes. So, so a point P in this space is denoted by actually three coordinates corresponding to those directions x, y, z. Now, on the other hand, since this point is lying on this space, and if I consider only this system of points, this set of points, now within this plane also, we may define another, say, coordinate system, which is restricted to the points on this plane. And on the plane, let us consider two orthogonal axes, and one of them, let me denote it as the x-axis, that is on the two-dimensional when this x-axis is different. I mean, we are following our conventional way of denoting. So let me put it as x prime and y prime axis. And this point is expressed as the coordinates of this system for this two-dimensional system. So it will have equivalent in
প্রফ
a
ডিজিটাল
two-dimensional
ভিএলএসআই
coordinate.
সার্কিট তুমি দেখছো শান্তনু স্যারের
I think some sound is
ডিজিটাল
coming. So, so this is the
আচ্ছা
so this is a two-dimensional coordinate of the same point, and these coordinates are expressed with respect to a coordinate system which is restricted within the S-plane. So now you can see that for this set of data points, it is not really required to express each and every point using a three-dimensional coordinate system. It is sufficient if you express them by two-dimensional coordinates.
এখানে তো মানে এখানে তো ভরা
আচ্ছা,
দিয়েছে না ওটা
from
বলা
the NPTEL, just no, your voice is coming.
একটু করা হয় সবাই তো করে এখানে দিচ্ছে এখানে যে যে ইয়েগুলো আছে কতগুলো
Ankita, I think
Yes, sir. I'm calling them. They're not picking up.
okay. Yeah, I hope now they have understood. Yeah, right.
না দেখো
So
এইগুলো তো চেক করা হয় করে তো বলা হয় ওদের করে দেওয়া হয় তো 5 সেপ্টেম্বর অবধি ফোরাম চেক করা আছে
this voice is
27 সেপ্টেম্বর অবধি
going to call. Yeah, their microphone should be
হ্যাঁ
muted.
এখানে দিয়েছে ফোরামে দিয়েছে আমি দেখছি এখন আমি ঢুকলাম এখন অ্যাসাইনমেন্ট নাইট ডাউট আছে কোশ্চেন অ্যান্সার এখানে ও স্ক্রিনশট দিয়েছে হ্যাঁ এবার তো আমি তো পেন্ডিং এখানে সিটেও দেওয়া আছে এতগুলো কোশ্চেন আছে এগুলো পেন্ডিং আছে আমি তো ওকে বলেছিলাম ছেলেটা মনে হচ্ছে
Anyway, so
চাকরি করবে
I hope
রোজিত হ্যাঁ আমি
we'll
দেখছি
continue with this.
রাজি এই তো
Right,
এখানে 27
so
তারিখ
this is
ঠিক করে
this is why the
জি।
dimensional reduction will be meaningful
এর আগের বারে তো
in such a
অ্যাসাইনমেন্ট
situation.
করে ও অনেক দিয়েছে মানে পরে দিয়েছে ওর মেয়ের খুব শরীর
It
খারাপ
is they are speaking very in a loud voice.
বলছিল আমাকে দাদা আমি এখন পাচ্ছি না
Yes.
দিতে
Let me
তাও
see.
বললাম দেখো লাল ইয়ে তোমার লিস্টটা কিন্তু একদম নাম রেড মার্ক পড়ে যাবে এরপরে কিন্তু অনেক অসুবিধা হবে এরপরে আচ্ছা আচ্ছা দেখছি বলে তাও দিয়েছে আর কি তো একদম ফোরামে নিশ্চয়ই অ্যান্সার দিচ্ছে না নাহলে আমি যেগুলো ফোরাম পঁচিশটা পঁচিশটা আজ অক্টোবরের 1 তারিখে একটা লাস্ট এসছে 25টাই আছে কিছু লোক অ্যাসাইনমেন্ট কোয়েশ্চেন নিয়ে দু একজন করেছে আমি দু তিনটা কোয়েশ্চেন দেখতে পাচ্ছি দেয়নি হ্যাঁ ঠিকই ঠিক এখন ও ছাড়া তো আমরা দিতে পারবো না আমরা রিমাইন্ড দিতে পারি সে না আমি আরেকবার ফোন করে বলবো যে যা অ্যান্সার গুলো আছে পরীক্ষার আগে একটু দিয়ে দাও পরীক্ষার আগে একটু দিয়ে দাও নাহলে এরা আবার তোমার নামেই কমপ্লেন করবে যে টিএ কাজ করছে না বলে ঠিক আছে আমি একবার ওকে ইনফর্ম করে দিচ্ছি কোশ্চেন আমরা কি অ্যান্সার দেবো বলো তো এই যে স্ক্রিনশট দিয়ে দিই সেগুলো আমরা অ্যান্সার দিতে পারবো আমি তো না এই যে ও দিয়েছে এই যে কোনো ক্লারিফিকেশন চেয়েছে
Okay, so let us see that how actually this what is the technique for expressing the same point by using less number of coordinates, or that is what is the dimension reduction. That means within this two-dimensional coordinate system, we can express these points. So we can find out those axes, we can find out the corresponding origin of this new coordinate system. And the principal components, they are the, so the directions of the principal components are basically these axes, all these axes. And the components itself are those particular coordinates, which are the factors along those axes. So this is the, from the outset, this is what we are going to achieve if we perform a principal component analysis. So what is the approach that we follow in that case? So what we would like to see here, while finding out particular directions on which you can capture, most of the, I should say, data's contribution. So that is a kind of intuitive way of saying that how the principal directions are to be found out. And once you get the principal direction, then you take the respective projection of a data point on that along that directions. Of course, you need to also set a particular center which should lie on that direction itself. So the problem is mathematically posed in this way. First, let us consider that what is say uh, I mean, one of the condition is that we define the variances. So what is the directions where the the variances of the projected data is maximum. So say I will, let me use this figure, or let me use a new figure. Okay. Say consider a set of points, and what is meant by the variances of this data set along a particular direction? You consider any particular direction. Now, when we say it is not only direction, we also consider a basically a straight line also, or rather, yeah, line passing through a point. A direction is also fine. Now you may consider a particular point on that straight line. Now you can see that this is your, say, in your new coordinate system, say suppose this is your center, and you have uh, a new coordinate system of x, y, z. So I am giving example with respect to three-dimensional coordinate system, and let there be one particular directions in that system. So when you take a projection, you know that this is the projected point. Okay. So if I take the perpendicular draw, and this length is the projected length. So it will have some value. Say if this is the data point 1, say consider this length is, say, L1. So there is a particular, you see, there is a reference point, and from which actually we are taking all these projections. So say this is another data point, and you have another projection. Say this is L2. This is the length for this second. And in this way, if there are n points, you have L1, L2 to Ln. Okay. So now what you can do, you can define the variance of these particular data points or projections. You can define a variance of these projections. So you know that in the definition of variance, it is basically the average of the square of distances. So if I say the mean is L bar and this is Li, so I will take the square because these are all scalar value. These are all lengths along a particular direction from a point. These are all scalar values. So like every variance is expressed. So if there are n points, so it is average of the square of deviations from the mean of this distribution. So this is the variance. So this is the variance associated with this direction. So in your principal component analysis, we would like to find out that direction, which is the principal directions, where this variance will be maximum. And before that, we put the center point as a mean of all these data points. So we come to the center of these data points, right? At the center of the data points, we find out the directions on which this variance would be maximum, right? So this is the kind of mathematical problem for which that the solution, if you go through the respective analysis and derivation in our slide set and also the lecture, if you go through that, we'll find actually this problem is reduced to finding the eigenvectors of the covariance matrix of this particular data. So the covariance matrix is defined as, you consider say this is the mean of the data, and say each vector, each data is represented as an n-dimensional vector, say x, and let me express it as a column vector, say x1 to xn. Okay, so n-dimensional column vector. So when we define a covariance matrix, we define it as x and x transpose. But before that, we subtract it from the mean. So it is the same. It is, x, what we'll do, we'll take the vector, we'll center adjusted vector. So instead of x, let me put it as a center adjusted vector. That means we are expressing this vector, the offset is at the center of the data point, which is x1. And now this is the covariance matrix of the data point C. Okay. And of course, you have to divide it by the number of data points. Then it becomes covariance matrix. Otherwise, accordingly, it should be scaled. If there are n data points, so this n, let me use the capital N here because small n is used for the dimension. So this is the covariance matrix. And your problem of finding out the principal directions of maximum variance is reduced to finding out an eigenvector. So we can consider a vector, say C, say E is the principal direction, and we consider this direction is an unit vector, right? That is the constraint we can put. So it should be expressed in this. Okay, where C is the covariance matrix. And so this solution, as we know, this is the solution of an eigenvector. You can get n eigenvectors, in fact, but for the directions of the maximum variance, you have to consider the direction where the eigenvalue is maximum, because these eigenvalues, they are providing you the respective variances. This eigenvalue itself is providing you the respective variances. And sum of all these eigenvalues will be actually the total variance of the data. So those are the derivatives. So once you get a particular direction, then again what you can do that you can uh, you can uh, take out the components, respective components from each data point. So that is called residual vector. Suppose you have this direction E. Say E is a solution, principal solution. So let me say rather E1, that is first principal no direction with the maximum eigenvalue. So now for any vector x, what you can do that you find out what is its, this is an unit vector. What is the factor? What is the contribution of x along E1? So we know that if I perform the dot product, we get respective factor. So this is the factor along this direction, and uh, this direction. So this is the vector contribution of x along the direction E1. So if I subtract this factor from x, I will get the residual x, residual of the vector x. So we can compute all residual vectors of all the data points. So this process can be repeated on the residual vectors. So again, for finding out the next principal direction, and which will be in fact orthogonal to E1, because E1 is orthogonal to all these residual vectors. So the next principal directions will be also orthogonal to E1. So again, you apply the same process and you can find out the next principal directions by finding out the eigenvectors of the covariance matrix of these residual vectors in the same way with the eigenvalue. Now, all these things will become equivalent. So you do not require really do it iteratively because because they are all orthogonal. So in fact, the covariance matrix, the original covariance matrix of the data points, center adjusted data points, they itself has all the principal directions, because if I get the n eigenvectors from the all n eigenvectors will provide me all the principal directions for this data point, and with decreasing variances along each directions, right? Which means that I will get n directions, say E1. These are n eigenvectors from the covariance matrix of the data points, and if I order them according to their decreasing value of eigenvalues, so I will get such n directions. Each direction is a principal direction, and now my coordinate system for representing the data point will have all these directions. So all n axes, they are along these directions, and their origin would be the center of the data point. So this is a new coordinate system. So it's basically coordinate transformation from n-dimensional coordinate to another n-dimensional. You see that here still the dimensional reduction did not take place. We have the same number of principal directions, same number of directions, same number of axes. So even if we represent the data point within this new coordinate system, it requires n dimensions. But what is interesting is that we get an ordering of these, importance of these directions. So this is the most important direction because this has the maximum eigenvalue. It is the maximum information bearing. And this is the list. So what happens if the data is arranged in a plane? As we know that it requires only for a plane, all the data points can be expressed by using only two coordinate axes which are lying on this plane, two orthogonal coordinates which are lying on this plane. So these two eigen directions are sufficient, and contributions along all these directions will be zero, ideally. So which means that I can ignore all other directions which have very small eigenvalues.
অঙ্কিতা স্যার কি শেষ করে দিলেন?
না স্যারের ওখানে লোডশেডিং হয়েছে,
ও ওকে, আচ্ছা আচ্ছা,
তো এক্ষুনি লাইট এসছে, পাওয়ার।
ওকে ওকে।
Okay, so we had a power cut. Um, yeah. I, am I audible now?
Yes, sir. Yes, sir.
Okay. Anyway, so I hope I have already discussed and is there any question? If there is any questions, let me know that what is the I should say there are various ways principal component analysis can be looked into. This is one of the ways we may consider that we are trying to capture the directions of, I should say, increasing variances uh, for representing a set of data points. It is not the single data point, it's the set of data points for which a set of directions are sufficient to represent in a Cartesian space, I should say, in the Cartesian coordinate, using the Cartesian coordinate convention, you can represent data points, and that is what is the dimensional directions. You require less number of directions, less number of, I should say, principal directions in the Cartesian coordinate convention. So, is there any other questions or any questions related to this?
No, sir.
Yeah. So should we close the session or from NPTEL? Yeah, I hope if there is no other questions, so let us stop here, and we'll have another live session. Uh, I think in the last week of October, the dates will be announced. And if you have any questions, again, we can discuss there. Please post your questions in the forum so that we know that what kind of queries you have, and accordingly, we can discuss those issues in this particular live sessions. So with this, let me close this session. Thank you very much.